All right, our next shape is trigonal bipyramidal. Here we have five electron density groups, and for the molecular geometry, all of them are atoms. So we have an X up here, we have an X here, we have an X here, and then we have one going into the back of the board, and then one coming out of the board, right? And trigonal bipyramidal makes sense. You've got a triangle right here, and then you've got a pyramid pointing up here, and you got a pyramid pointing down here, right? So it's trigonal and with kind of two pyramids. In this case, we have two different bond angles. The one from the top to the bottom here is only 90 degrees, whereas the one in the pyramidal part, or the trigonal part, my bad, the trigonal part is 120 degrees. So these actually get different names. These two up top and bottom are called the axial, right? Just like the Earth, the axis of the Earth, it's the top and the bottom. And then these three within the plane of the board, or my bad, these three are called equatorial, right? Just like the equator of the Earth. An example of that is PCl5. And of course, you can take a look at in this bonding. So let's get rid of some of these lone pairs. And then we'll add 1, 2, 3, 4, and then we add a fifth one, right? So you can see that you kind of have these three, right? There's your trigonal part. And then you have one on the top and bottom. If you connect all the lines, you kind of make a pyramid. And if you take a look at the bond angles, all of these are 90, whereas these ones up here are 120. And then, of course, we start taking away atoms and start replacing them with lone pairs. If you do it this one calls it a sawhorse. That's one option. You can also call it a seesaw because it looks like a seesaw. And so the interesting point with the seesaw or the sawhorse is now we have a choice of which one we're going to replace. Are we going to replace one of the axial or one of the equatorial atoms? Well, if you think about lone pairs, they're larger than bonds, so they're going to want to take the place of the thing that has more room to kind of be. And that'll be the equatorial position because it has those 120-degree bond angles as well. So it allows that lone pair to kind of be a little bit further than everything else. Example of this is SF5. F. And of course, you can make it here too. Take away a bond, add a lone pair, boom. And you can see how it looks like a seesaw, right? If you place it right there, and then if it were to kind of, I don't know, I can't make it rotate like a seesaw, but you can see how it looks like a seesaw, right? A kid sitting on the left and the right side, and then they go, play on it. After that, we take away two lone pairs. This is then called T-shaped. And shocker, it looks like a T. So now we're going to replace two of our equatorial atoms now with lone pairs. The example of this is BRF3. And one of these lone pairs is going into the board. One of them is coming out of the board. It's going to take away another bond, add another lone pair. There we go. And then if you organize the molecule kind of like that, you can see how it looks like a T. And then finally, if you remove a third one, then you go back to being linear. Right? Because you only have the axial atoms left. The example of that is XeF2, right? We have xenon bonding. So remember we said halogens rarely bond, but it doesn't mean that they don't. It just means that it's relatively rare. Right? And if you think about it, it makes sense. Take away a bond, add a lone pair, boom, we're back to linear if we think about the molecular geometry.